So our next speaker is Vikrant Singhal.
Right. Yeah. Right. Am I audible? I think I am. Okay, cool. A bit closer? Better? Okay, cool. All right, so as announced, I'm Vikrant, and I'll be talking about private estimation of certain high-dimensional distributions. Okay. In our paper, we deal with two distributions, multivariate Gaussians and product distributions over binary strings of length d. But I'm only going to focus on Gaussians in this talk. Our main results are that we learned both these distributions privately for free, which vaguely means that our algorithms are as efficient as their non-private counterparts in terms of sample complexity, runtime, and requiring pretty weak constraints on the distribution parameters. Good. So I'm going to start by introducing the notion of private distribution learning. We have an unknown distribution P from which we can sample as many points as we like, and our goal is to privately estimate P, which means that our algorithm must satisfy two properties. First, accuracy, which means that if the samples are coming from P, then with high probability, our algorithm must output an estimate Q, which is at most alpha, far away from P in total variation distance, whilst using as few samples as possible. And the second goal is privacy, which should hold for all samples in our dataset, always, regardless of the distribution they're coming from. A little more formally, we want our algorithm to be differentially private, which means that for any pairs of datasets which differ on at most one sample, the output distribution of our algorithm, mx and mx prime, should be pretty close. Now, this sort of privacy is usually quantified by some parameter and is typically achieved by adding some random noise that is large enough to mask the effect of any single sample in the worst case, or what we call the sensitivity. Okay, so now going back to the definition of privacy again, there are multiple ways of defining the closeness between mx and mx prime, like in the original differential privacy definition. But the one that we use in our paper is one of its subsequent versions called zero concentrated differential privacy. Now, you don't really have to remember this definition for the purpose of this talk, but all you have to know is that it's quantified by a parameter rho, and it's slightly stronger than the more well-known epsilon delta DP definition. Okay, so let's first talk about some challenges to estimating privately. As I said, we need to add some random noise to mask the sensitivity. But in order to calibrate that sensitivity, we usually need some kind of bounds on the range of the data or the distribution parameters, or what we call the range parameters. Now, the trivial algorithms tend to have linear dependence in their sample complexity to achieve any sort of non-trivial accuracy, which implies that they need strong a priori knowledge about the data or the distribution, which could be pretty unrealistic. So one of the main challenges is to reduce this dependence on these range parameters, which is what Karva and Vedant did in 2018 for the case of one-dimensional Gaussians when they had essentially no dependence on these parameters. So now one might think that even if you have private efficient algorithms for the case of one-dimensional problems, isn't it possible to directly extend them to higher dimensions? The answer is it's not always so trivial. Often doing that incurs huge costs in sample complexity in terms of both the range parameters and the dimension, which is what happens in case of Gaussians as well. So all that makes our problem so much more interesting to solve. Good, so I will now describe the problem and our results a little more formally. We have sample access to an unknown Gaussian, and we need to output mu hat and sigma hat such that the total variation distance between the two Gaussians is at most alpha. Now, there is a non-private algorithm which does that using d squared over alpha squared samples, but we want to do this privately. So we come up with the rho-z CDP algorithm, which does that privately using d squared over alpha square root rho additional samples. But that's not all. As I said, we need some range parameters as well. So we need to know parameters r and k such that the mean mu lies in a ball of radius r around the origin, and all the eigenvalues of sigma, or the directional variances, lie between 1 and k. Now, there are two key features of our sample complexity. First, the dependence on the dimension and alpha in the private side is no worse than that in the non-private side. And the dependence on the range parameters r and k is fairly small, polylogarithmic, which means that we need really weak prior knowledge about the distribution parameters, which is what we had hoped to achieve at the beginning. So before I move on to our techniques, I'm going to first describe what it means to learn Gaussians in total variation distance. Now, note that Gaussians can be represented visually by ellipsoids. So to be accurate, two things should happen. First, the ellipsoids representing the actual Gaussian and our estimate should look similar. That is, each directional variance of the actual Gaussian should be estimated to within a small multiplicative error, and the alignment of the two ellipsoids should also be similar. The second requirement is that the centers of the ellipsoids should also be pretty close to one another. That is, the means should also be pretty close to each other. Now, this is especially tricky in case of differential privacy because, as I said, we need to add some random noise to get privacy. But we somehow have to make sure that the noise we add in directions with small variances is much smaller than the noise we add in directions with large variances, despite having no prior knowledge about the shape of the covariance. So let's see how we do that. I'm going to start with a naive algorithm for covariance estimation. Without loss of generality, I'm going to assume that all points are coming from a zero mean Gaussian with covariance sigma. And this is because we can take 2 points from the original Gaussian, take their difference, and rescale them to obtain a point from zero mean Gaussian. This is a pretty standard technique. And now the naive private algorithm is just to output the noisy empirical covariance matrix. That is, calculate the empirical covariance matrix, and to each entry, add independent noise sampled from this one-dimensional Gaussian shown below. Now, this is more commonly known as the Gaussian mechanism and is differentially private. But the more important thing here is that it requires kd squared samples to be accurate, which is fine if k is a constant. But if k is slightly large, even a small polynomial in D, it really messes our sample complexity up. So ideally, we would like to work with a Gaussian that is almost like a sphere, such that we have a constant factor approximation to all its directional variances. So we come up with this new technique called private recursive preconditioning, which privately transforms any Gaussian so that it's now almost like a sphere. That is, its eigenvalues now lie between 1 and 1,000. So once we have this preconditioner, we can just shrink down any Gaussian to make it sphere-like, estimate the shrunken distribution using the naive algorithm, which now does not require too many samples, and then stretch our estimate back using the inverse. So the question is, how do we get such a private preconditioner? As the name suggests, this is a recursive algorithm, and in each round of the recursion, we obtain a super rough estimate of the covariance called sigma hat using the naive algorithm, but with very few samples. And then we get a projection matrix out of sigma hat, which scales its large eigenvalues by a constant factor. Now here's what happens. This estimate is far from being accurate, but it's still good enough to give us enough information that we can distinguish the long directions of sigma from the short ones. That is, the directions of sigma hat which appear long cannot be too short in sigma, and the directions of sigma hat which appear short cannot be too long in sigma. And because of all this, this projection matrix essentially scales all the eigenvalues of sigma, which are more than 0.5k, by a factor of 0.7. So we can move on to the next round of recursion using 0.7k as an upper bound. So yeah, that's it for the preconditioner and covariance estimation. Mean estimation is pretty straightforward using prior techniques once we have an accurate estimate of the covariance, but that's not something I want to talk about today. Yeah. So that's it for estimating Gaussians. To conclude, we have both upper and lower bounds for private estimation of high-dimensional Gaussians and product distributions. There are a couple of open questions. Is there any epsilon delta DP algorithm for learning Gaussians with absolutely no dependence on range parameters R and K? And for what other high-dimensional distributions could we get privacy for free? That's it. Thank you. Oh, and poster number 164.
Questions for Vikram?
Yes. I'm sorry, what? Oh, this technique, I think so far we have tried it with Gaussians. It works with Gaussians, but we haven't thought about other distributions yet. We apply similar techniques for the case of product distribution as well. Not the same, but something similar. Yeah.
Quick question. Do you also get height estimates in for estimating this distribution in tail divergence?
Not for high-dimensional Gaussians, but for product distributions we do. Yeah. Right.
Let's thank the speaker again. Should I say that you need no introduction, or you do? Okay. Anyway, our next speaker is John Ducci.
All right. Thanks for sticking around. Okay, so I'm going to talk about some recent work that I did with Ryan Rogers, who was working at Apple, on optimality, local privacy, and connecting these with communication complexity. Wrong button. Okay, there we go. So what is local privacy? Local privacy is essentially that we, providers of data, who we'll call x1 through xn, pass their data through some kind of privatization scheme before a statistician or a learner gets to observe the data at all. All right, so in this picture, you can think of the statistician or the learner or the method as script m. It's going to spit out some estimator theta hat of some quantity or other. Before you get to observe, before the method gets to observe the data, it goes through this channel Q. Do I have a mouse? Does this work? There we go. Goes through a channel Q. It does work. Goes through a channel Q, gets privatized to become ZI. Okay, so that's kind of the game in local privacy. And then the question is, how do we develop optimal estimators under sort of constraints of this form? And I'll make this a tiny bit more rigorous. So the model of local privacy I'm going to work in, I can represent with this very clean picture. Okay? So what is this saying? So what's the game here? So the game is that we're going to allow communication and things like this of private data to happen in a fairly sophisticated fashion. So what happens is we proceed in a series of rounds, okay? And in round 1, person 1, that's x1, generates some data z1, 1, okay? And then it's person 2's turn to generate some kind of data or release some sort of privatized statistic. This can depend on the previous data releases, so that is to say that z2 can depend on z1, and it depends, of course, on x2. We repeat this, you know, through all n participants in our study or our learning or whatever, and then we aggregate all of their data into what I'll call a blackboard. So that's the blackboard B1. So this is kind of the standard blackboard model of communication, if you're familiar with this. Okay, and then we can have another round of communication or private data release or whatever you want to call it, and in that round, call that round 2, you know, person 1 releases Z1 superscript 2. That can depend on all the previous data releases and everything else, and we just continue this strategy on and on and on. Okay, and then this could go in rounds. You know, you could go round 3, round 4, etc. So it's kind of the communication mechanism scheme clear-ish. One person says, yes, that's good. Vitali is at least listening to know that I asked a question, so excellent. Okay, so then the definition of privacy that we're going to work in is, well, we'll see actually a bunch of different definitions of privacy. The starting one is local differential privacy. So we say that this whole channel or this whole communication scheme, whatever you want to call it,